Okay, let's begin. Let's talk a little bit more about adding stuff. We're still in appendix E. Last time we ended with the fact that if I wanted to find the sum of the first n positive integers, then that was actually this expression. Okay? And you can figure that out by adding the sum in two different directions, and then you'll notice that you would have n numbers of the same number, and then multiply and divide both sides by 2. So I showed you how to derive that. But there are several more rules that I want us to know, and I don't want to derive all of them, because it might be annoying. I don't want to spend the time. But other rules. It turns out we can also add the sum of the first n square numbers. Okay, so that means you're adding 1 square plus 2 square plus 3 square plus 4 square plus 5 square plus 6 square, etc. That one is a little bit longer. It's n times n plus 1 times 2n plus 1 all over 6. You also have a rule that tells us how to add the first n cubes. So if you want to find the sum of 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed going up to n cubed, that one is, interestingly enough, is the square of this one. Okay. So these are some forms we should know. So these are kind of harder to derive, so I'm not going to do them. Some other rules I want to give you, though, that are pretty obvious. Let's say I wanted to add n terms of a constant. Okay, so that one you should be able to see pretty easily. This is just like me taking each output of our function, the a sub I, is just going to be a constant c. So it's like I'm adding c for n equals 1, then add c for n equals 2, then add c for n equals 3, blah, blah, blah. You'll end up adding n c's. And so if you take the summation of a constant, that just gives you the constant times n. And so that's also a rule. I want to tell you those 4. And we also want to talk about some behaviors of these sums. So these are formulas that you should know. So this is 1, 2, 3. This should have been 1, but it was more exciting to start with this one because it had a story behind it. You know, like this one has a story. The others are just like, okay, mathematical induction or whatever. These are some formulas that you can do. You can add in several situations, and you're going to see the magic behind using these pretty soon. But other than that, there are some properties. And usually when you talk about the properties of something, you're talking about the algebraic properties. Can we add 2 summations? Can we multiply 2 summations, etc.? So properties of summations. It turns out multiplying 2 series is actually quite difficult, but we can add 2 series pretty easily. So, and we can actually multiply a series by a constant pretty easily. So here C is a constant. So here's an idea. If you actually have a series and you want to multiply it such that it's a constant times some formula that's giving you the ith term. Then it turns out that you can factor the constant out. Kind of like how you can do with limits and derivatives, the same idea will work for summations. You can factor the constants out. So, but why is that? This just means you're taking c times a1 plus c times a2 plus c times a3 plus da da da, c times an, common c, you can just factor it out, a1 plus a2 plus da da da, an, and then this guy is the summation of ai. And so you can always factor out a constant. You can also, finding the series of a sum, say I have one formula ai plus or minus another formula bi, it turns out that the summations will distribute across sums. So you can add two summations simply by taking the sum of the addition of the formulas. And that one is pretty much, it's because if you have a1 plus b1 plus a2 plus b2 plus dot 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 an plus bn, basically you can just regroup. You can choose that you can add all the a's and then add all the b's, because addition is commutative, so you can just arrange it so that all the a's come first and all the b's come second, and then each of these are summations. So you can factor constants out of summations, you can distribute summations across sums, so that's pretty neat. Those are two. To actually multiply summations, it's not as clear. The summations do not distribute across products, and it's not hard to see that, but you do have to think carefully about what the summation sign means. So, I should put this in right. Summations do not. Let's see these do not distribute across products. So if you're looking at the summation of something like ai times bi, right? You can't think of that as the sum of ai times the sum of bi, because that's not going to be the case. So this, you have to realize, means a1 b1 plus a2 b2 plus a3 b3 plus all the way down to an bn. While, if you look at this kind of expression, which you'd obtain if you thought of you could distribute across a sum, you should notice that what you actually get is the first part is just adding all the a's. And the second part is adding all the b's. And then you'd have to actually do a distributive law, and you will get a lot more terms than you get here, right? So you won't just have the a1 times the b1 and call it a day. You'd have a1 times b2 times b3 times b4, which do not appear here. So these two are not equal. They're not the same. You can't just have a sum, a formula, and then distribute the summation across those two formulas. So that's important. But with scalar multiplication and addition, things work out pretty nicely. Products are far more difficult. That's something you probably talk a little bit about in Calc 2, because you're going to be doing double integrals there, and that's kind of a separate situation. So we have those rules you need to know, the properties you need to know. I will show you some examples of us applying these guys. Or I'll show you one example where we're applying this, and then I'll show another example of a very cool situation. Then I'll talk about what it would mean to add an infinite number of things, right? We're going to kind of build up. So let's do an example. I'll probably want more space in here. For example, suppose you wanted to add up a bunch of things that looked like the following. 1 up to 100. You want to add 100 things that look like that, right? So you're going to have 2 minus 1 plus 1 added to 2 times 8 minus 4 plus 1 added to 2 times blah, blah, blah. You can just imagine you're adding up 100 things like this. Now, if you do that brute force the way you're normally used to adding, it would take forever. But with the summation idea and the formulas that we have, we can do this relatively quickly. So the first thing is to realize that it does distribute across the sum. You can also realize that I can factor this number out. The other two I don't need to factor anything out. And I'd end up with that. And so now I have formulas for each of these. So I can know that this guy is going to be, now inside my n is 100, so it's going to be 2 times 100 times 100 plus 1 times 200 plus 1 all over 6 minus, oh, this is the cube, sorry, I thought that was the square. The cube formula is actually n times n plus 1 all over 2 squared minus, for I squared, that's n times n plus 1 times 2n plus 1 all over 6. So this is going to be n times n plus 1 times 2n plus 1 all over 6. And then this will be, this is just a constant, so it's just going to be the constant times n, it's just 100. It turns out if we were to add up 100 such expressions, add up 100 of these, this will be what you would end up with as the result. And so pretty much that would be 100 squared, 101 squared over 2. 100 times 101 times 201 over 6 plus 100, which is whatever. You can transform it. I'm just showing you an example. Right? So you could ultimately get to that that answer if you wanted to, with in a much quicker way than it would take you to actually add up 100 expressions of this form. So this is how this notation becomes very useful, becomes very efficient after a while. Once you take into account all these properties and theorems that we can derive. Not only can we do things quicker, but we can actually write a shorter notation for it. I don't have to say what I'm adding is this plus that plus dot 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 plus da da da. I can just write boom, and that means the same thing. So we get a shorter notation and we get an efficient way to add things. Now here is a cool situation. And you'll, again, see this a lot in Calc 2, but there's something called a telescoping series. I'm not sure why it's called a telescoping series. But basically, this is a series in which all by finite number of terms will cancel out. So it looks like you're adding up a lot of things, but you're really only adding up a few things. So an example of that, an example of a telescoping series. You can consider the following. And here I'm doing I from, let's do 1 up to n. I put a number here before, like 99, but let's actually just make it n. Let's make it go as long as we want it to. Let's say I wanted to add up n such terms. Now, you need to notice that we have a formula for to compute I and I plus 1, but not 1 over I. If a summation doesn't distribute across a multiplication, it's not going to distribute across a division. So it's not like you can apply the formula in the top and bottom. That will actually be incorrect. So you might start out by, let's just start plugging things in and see how it looks. You'll notice that the first term would look like what? See if you remember how to read these things. So this is 1 over I. This is an I here.
I to the negative 1.
Come again?
Are you asking like to rewrite?
I'm asking you to, no, not to rewrite this, to like, I'm writing out the terms now.
Oh.
So what would the terms look like?
1 minus 1/2.
1 minus a half, plus, so that's when your I equals 1. Then we can do for I equals 2, that's going to look like what?
1/2 minus 1/3.
1/2 minus a third. I equals 3, you're going to get a third minus a fourth. I equals 4, you're going to get a fourth minus a fifth. Plus, okay, then you keep going. And let's say we're on the tail end of this summation now. Let's say I'm at I equals n minus 3. And then I'm going to look at I equals n minus 2. Then I equals n minus 1. Then finally I equals n. Okay? So now the n minus 3 term would look like 1 over n minus 3 minus 1 over n minus 2. Plus 1 over n minus 2 minus 1 over n minus 1. Plus 1 over n minus 1 minus 1 over n. Plus 1 over n minus 1 over n plus 1. So I'll add a bunch of terms and you'll notice that starts happening. Now what you're also going to notice is that the second term in each sum will actually cancel out the first term in the following sum, right? It's not always right behind each other like this. Sometimes it might take a while. Like if I put I equals 2, I plus 2, it would cancel out every second sum, or I plus 2 would cancel out every third. Anyway, you might see a pattern like this, where now you realize, oh, minus a half, plus a half, minus a third, plus a third, minus a fourth, plus a fourth, minus a fifth, plus a fifth would end up right after that. Then you're going to keep going. Obviously, this guy will cancel that, this will cancel that, this will cancel that, and you'll notice that this guy will cancel with the minus 1 over n minus 3 that would be from the previous term. So it starts out being this huge sum, but what you will notice for this guy, everyone cancels out except the first and the last number. Right? So essentially, this entire sum becomes just 1 minus 1 over n plus 1. And that will be the answer. Okay? This is called a telescoping sum, whenever you see a pattern like this, right? So you're summing a bunch of things, but they're just so off the form that they'll cancel themselves out. So this is an example of what's called a telescoping sum. So those are, you have really cool situations like that. So you'll do a lot of series stuff in Calc 2, so I don't want to spend too much time on this. I want to get to like the calculus, get back to calculus. But summation is something you're going to need to know a lot about, especially if you want to do anything worthwhile in mathematics eventually. So any of you are going further, you're going to do a lot of things about series in Calc 2. You'll do things with series in differential equations. You'll do things in series with advanced calculus, with real analysis. Summation is actually one of those things that are, it's everywhere. Like being able to add up a lot of things is something that we always need to know how to do, it turns out. Okay. I want to segue into this example. Now, we're going to consider a question . Now, we actually knew that it was possible to add an infinite number of things and get a finite answer for a long time. This goes back to, I mentioned this before, and I said I forgot what the name of the person was that thought about this, and I said I was going to look it up for my next class, and I forgot to look it up. It's a part Aesop, his name starts with A. Someone remind me to look that up. Okay. So the thing is, he was considering a very strange question. He imagined someone, shooting an arrow at a target, right? And he's decided to get all philosophical with that example, right? So he said, what if you imagine we did the following, right? So someone can shoot an arrow at a target, boom, and they'll hit the target. And then he said, what if you actually dissect it this way? What if you always freeze time when the target has covered half its distance, right? So if you're 100 feet away, we'll freeze time when the arrow is 50 feet away. Then we'll then freeze time when it's 25 feet away. We'll then freeze time when it's 12.5 feet away, and so on and so forth. So he's pretty much always considering the arrow as being in a position that's half the distance left to be covered, right? So then he's like, well, if the arrow can always only travel half the distance it's about to cover, will it ever get to its end destination, right? So if you're anywhere and you want to get here, but you're only allowed to cover half of that distance, how are you ever going to get there? You're always only covering half the distance between you and that thing, right? So it's like, clearly we should be able to freeze time and actually do this, right? And it would seem that, the arrow would never actually hit the target, but we do know it actually hits the target. You do actually cover that 100 feet, right? And so that was a paradox that he couldn't figure out, and this was in the BCs, right? Way a long time ago, right? So there was this idea that you can take like adding up an infinite number of quantities, like half distances, and it seemed to make sense in physical reality that should add up to some number, right? You should be able to add up an infinite number of these half distances, and it should total the 100 feet that the arrow actually covered. And so it wasn't just something that we just thought, if you add up an infinite number of things, it's going to be infinity. What else could it be? No, it turns out you can add an infinite number of things and you can get a finite number. And reality would suggest that that is the case. So now the question becomes, how do you actually do this? It seems to be possible, but how do you actually do the math behind it? So here's what we can say here. When we try to figure out the math behind how the arrow actually hits the target, we considered the concept of what we call a partial sum. we often call it the nth partial sum. Now, I'm going to tell you what a partial sum is. Okay. So you might have a summation doing I goes from 1 up to big N of some expression. Okay? And that's going to add, you know, A1 plus A2 plus A3 plus plus A n minus 2 plus A n minus 1 plus A n. Okay? So it'll add up to all these terms. Now what the partial sums are is you actually take the sum of the first n terms leading up to the big N. So there's something called the first partial sum, which is going to be this guy. Let's call that S1. Then there's something called the second partial sum. That was the sum of the first two terms, S2. Then you'd have the third partial sum. That's the sum of the first three terms. Then the fourth partial sum. That's the sum of the first four terms, and etc. And you're considering these list of numbers. So we define S of n, the nth partial sum, to be the sum of the first n terms of the series. Right? So that means you can have S1, it'll just be A1, while S2 is going to be A1 plus A2. S3 is going to be A1 plus A2 plus A3, and so on. And so you're going to have Sn is going to be the A1 plus A2 plus all the way up to An. Okay? So these are called the nth partial sums, and you can essentially keep going if you must. Okay? Now what you'll realize is that this becomes a list of numbers that you can talk about, and this list of numbers will have this list. Will have a limit if the sum is defined, that is. And what do you think that limit would be? Well, ultimately, if you're doing a finite sum, the biggest partial sum you can get is the sum of all the terms. So the list will terminate, it will end at just what the entire sum was. Okay? So the limit is going to be the sum of the terms. And you'll notice that the partial sums will get closer and closer to that limit. So, for example, we knew that, okay, so let's say we wanted to add up the first 1,000 integers, the thing that they had baby Gauss do. Then you can consider the numbers, okay, 1, and then 1 plus 2, and then 1 plus 2 plus 3, and then, right, you're considering these numbers. And your goal is to reach to 1,000, which is going to have 1 plus 2 plus 3 plus all the way to 1,000. Now the idea is, these numbers will successively get closer and closer to what this answer is. Okay? So here you're 1, you're super far from 1,000. Here you're 3, a little bit closer to 1,000, but still pretty far. Here you're 6, we're getting closer to 1,000, still pretty far. You keep going. Eventually, you'll hit the target. Okay? So you kind of did what that guy thought of, right? You cut the journey into some discrete parts, right? So we could cover 1,000th of the journey, then 2,000th of the journey, then 3,000th of the journey, and we keep going. And eventually you're going to hit that sum. Now, we can actually imagine that our n is going off to infinity. So what you actually do is you actually define, and this will actually work out if you kind of do the experiments where you consider these paradoxes, like the paradox I was talking about, and you do that thing where you're doing half distances, and you use the theorem that I'm about to tell you to compute what it would mean to add up an infinite number of these half distances, you'll actually get the distance that you were supposed to get in reality. So we know this works. And so we define the sum of an infinite number of terms, AI, to be the limit of a sequence of partial sums. So basically what you're going to do is you're going to add up the first n things. And you're going to keep successively adding up the n things. And what you're going to do is you're going to essentially do this forever. You're going to let that n approach infinity. So you start this process, and you just allow the process to run forever. Right? And we have a limit for that. That limit as n approaches infinity will describe that process. So you're creating a list of these things that are running forever. And so what you can do, figure out how to add the first big N of these things, and then let that approach infinity. And of course, with the formulas that we have, doing this is not a problem. And of course, with the first part of the course that we did, we know how to compute limits. So ultimately, we have all we need to actually add up an infinite number of things. So I can say here, what if I wanted to do this example? And we're going to tie this into areas pretty soon. So here is an example. We're getting super close to being able to apply this now. Suppose I actually wanted to find I goes from 1 to infinity, so I'm adding up an infinite number of terms now. I want them to look like this. I want to add an infinite number of expressions like that. Okay, now let's make sure we understand what this means. We know how to read this. Remember, the variable in our summation is indicated by the index. It's telling you I is going from 1, 2, then 3, then 4, then 5, and you keep going. I is going from 1 to infinity. Okay? The n itself is not being moved, right? As far as this summation is concerned, the n is a constant. Okay? But, so essentially we're just moving the I. So we have 1 over n times 1 over n squared plus 1 over n times 2 over n squared plus 1 over n times 3 over n squared plus, keep going. Okay? So we want to add up an infinite number of expressions that have this form. Okay. Now, will that actually give us a meaningful answer? Well, for this particular example, it turns out yes. Now, it doesn't always give you a meaningful answer. I should say that. There are times when you're adding up an infinite number of things and it goes off to infinity, or it goes off to negative infinity, or it can actually go to nothing. You can actually have a sum where it doesn't make sense to put a value on it. It's not a number, it's not infinity, it's not negative infinity. You just say it doesn't exist. Right? Common example there is an alternating sum, like you're adding 1 minus 1 plus 1 minus 1 plus 1 minus 1. It's like, okay, sometimes it's 0, sometimes it's 1, but it never actually settles anywhere, right? So you can have all sorts of situations. In this particular situation, you can get a number. You will talk about all the other kinds of situations in Calc 2. So let's actually do this one here. So I want to compute an infinite number of terms that looks like that. And by next class, we're going to apply these ideas to actually finding area. So here's the first thing. So I have that, I want to actually rewrite it a little bit. I can do that. Now I have the property that says I can factor out constants. I is my variable according to this series. That's the thing that it keeps changing. N is pretty much just going to sit there. So I can think of my n as a constant here, and I can factor that out. And so now, what does it mean to add up an infinite number of squares? Well, by our definition, this is going to be the limit of this guy. So I index it by n, and I'm going to let n go off to infinity. Now what's going to happen is, here I'm going to have that. For this guy, what is the sum of I squared? It's n times n plus 1 times 2n plus 1 all over 6. It's kind of too quick to have you memorize that, but you should memorize those formulas that I mentioned earlier. They should be memorized eventually. What would this limit actually be? So that's the limit we should be able to find. What is it? Huh?
Is it 1/3?
It's 1/3. How do you know it's 1/3?
Distribute and then infinity rules.
Right, so the top will give you 2n cubed something, and the bottom gives you 6n cubed. The highest power on this is the same on the top and bottom. You go to the ratio of coefficients. So it goes to 2 over 6, which is 1/3. So it turns out if I add an infinite number of things that have this form, it actually adds up to 1/3. It is weird, yes. I can add an infinite number of things and get 1/3 as the answer. So, I should have phrased that a little bit differently. I should have phrased the problem a little bit differently. Because I never really explained why you'd want to stop at n here. There's an example. We can actually use limits to add up an infinite number of things. So we apply the rules that we know from about summations, how sums behave. And if we want to add up an infinite number of things, all you have to do is use a limit to help you add up an infinite number of things by adding up the first n things and then letting that n go off to infinity. And that's the same as you adding all the partial sums. Essentially going on forever. And it turns out that even though you're doing this forever, you will approach the number 1/3. Or I guess I'm more interesting examples here too. The examples I'm thinking about, I'd have to actually tell you a lot of other stuff to be able to say that. Okay? That's kind of all I wanted to do with summations. So I told you the formulas, I told you the properties, we did those examples, and now we know how to add up an infinite number of things. Okay, cool. In a finite number of time, in a finite amount of time. I don't really have time to go into much more. Now I'm going to build this up better, but to consider for next time. And now I'm kind of introducing the idea I'm going to talk about next time. It's called taking Riemann sums to find the area under the curve. Suppose we have a curve x squared. And I wanted to guess what is the area under this curve between, say, 0 and 1. Right, so I want to approximate this area here. Of course, that's a very weird shape. I don't know how to talk about the area under that shape, not yet anyway. So instead what I do is I do our dissection idea. And I'm going to talk about why we would do the dissections the way I'm about to do it. Because I believe in the last example, we did sort of a patchwork of things. Right? But here, I'm actually not going to do any horizontal slices, I'm only going to do vertical slices. So I'm going to slice this thing up into, say, 4 slices. And so the area of that is really the area of these 4 pieces. And I still end up with a problem. The top of those pieces is a weird shape that I really don't know how to find the area under that shape. So what I do is I instead, let me do the following. Let me look at where the lines touch the shape. And I will define that as the height of a rectangle. So now you'll notice, I will now have, essentially the first rectangle has height 0, so that actually doesn't put it in play. But if I look at the area of these guys, it's going to be an approximation for the area under the curve. Now obviously it's not going to be perfect because, look, I'm missing a lot of chunks here. So this will give me actually a smaller number than what is under the area of the curve. But you could imagine if I were to throw in more rectangles, I'd be able to fill in more of the gaps, right? And I could be able to do this for a while. We'll talk about that pretty soon. But we can do that. And now I can talk about what would it mean to add up the lengths of these rectangles, the areas of these rectangles. So I want to approximate by finding the sum of the area of these rectangles. Now, admittedly, it's not going to be perfect. I'm actually going to get a smaller answer than I should. But this process is called taking a Riemann sum. So it's taking Riemann is named after a mathematician. And this is his process of integration. So the process of integration that we use is actually pretty recent. This is late 1800s, early 1900s. He actually developed this way of integrating for his PhD thesis, believe it or not. So there are actually many ways you can integrate things, many ways you can find areas under curves. But Riemann pretty much developed this way. And so what you'll see here is the area is going to be pretty much the sum of the area of the first rectangle, area of the second rectangle, area of the third rectangle, area of the fourth rectangle, where AI equals area of ith rectangle. Now, how do you actually go about finding the height? Well, you pick numbers for these guys. Say I call 0 x1, this would be x2, that would be x3, this would be x4, that would be x5. Maybe I should start at 0, 1, 2, 3, 4. Now, let's say I evenly space these so that the distance between these guys is just some change in x, which I can denote by delta x. So I put this up to be evenly spaced, just to make life easier. And clearly, what would be the height of the rectangle in each of these cases? Well, if I know the x value, I can just figure out the height by plugging it into the function. Right, so this is really going to be f of x1. The height of this rectangle is going to be f of x2. And the height of this rectangle is going to be f of x3. So it turns out that my approximate area, let's not forget that this is an approximation, is going to be, well, technically it's going to be f of 0 times delta x plus f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x. Delta x is a common term, so I'd be able to factor that out. All the way down to f of x2. I'm sure how much writing that's it. Now it turns out that I can actually express this idea as a summation of things, right? Now I might do this if I'm computing by hand, but if I wanted the machinery to help me, you could just notice that I'm adding up things of this form. Where my I is starting from 0 and it is ending at 3. Right? So you can notice I can imagine this process where I'm approximating the area under a curve via the area of rectangles that I can erect. By touching that curve, I can pretty much take length times height for all of them, and I can add them up. A nice shorthand way to write this is an expression like this. This kind of expression is called a Riemann sum. It is a finite Riemann sum because this will only add up 4 things. However, we are going to push the limits with that, pardon the pun, and we're going to figure out the area under x squared pretty much next time. So we'll stop there. Just give you some ideas to think about. So that's where we're going.